My name is Abhishek Malik. I live in Munich, Germany, where I work as a data scientist at Hawk.ai. I'm very excited to speak to you about new ways of finding planets using machine learning. One main point I would like to highlight is why the bigger model is not the best choice always. And sometimes classical machine learning methods can be very efficient if used properly. Thank you. Looking forward to speak to you. So today we are going to talk about exoplanet detection using machine learning. And let me give you guys an idea how do we actually find planets. If you have a star system and if there's a planet present, and when the planet revolves around the star, and it might block some of the brightness of the star. And then we will see something like this on the right hand side. We'll see a dip in the brightness of the star. Now, by looking at those dips, we find out how many planets are there in the star system, how big are the planets, and how frequently do they revolve around the star, like what is the period of the planet. Now, looking at every single star by hand is a really tough job. So we need an automatic system which can look at those dips and tell us if there are planets present or not. Now, this is slightly more tricky because these curves can be in the different shapes. For example, in the first one, if the planet is really small or the star is really huge, the dip will be barely there, like it's a very small dip. On the other hand, the location of planet with respect to star also might change things. If the star is small, for example, like this, you can also have a dip which is deeper, and so on. So we need a system which can look at all kind of dips and tells us if the planets are there or not. So you will hear the term light curve often in this presentation. So let me just give you an idea what does that mean. So when we look at the star for a prolongated period of time, we will have a time series of the brightness of the star. And time series might look like this, and that is called the light curve of the star, as you can see here. But before we can do any kind of machine learning analysis or any analysis for that matter, we need to we can see that the light curve we see is very messy looking. So first step would be to take care of the errors we have, or take care of the unnecessary information we have. For example, we see that there is a trend in this time series. This trend is caused by the variability of the star. As in, a star might fluctuate between high brightness and low brightness states, and we don't want that information. It's not relevant for us. So we want to remove that. So first is to remove the trend of the light curve. Now, second, we see peaks here, small peaks here and here. Those are the peaks that might be caused by, let's say, gamma rays, and we don't want that in the data as well. So we need to remove that as well. And lastly, as we know, stars have different shapes, different size. Some are more big and small, and for that matter, they are also some of them are more bright than others, and hence the scale of the flux on basically the scale of the brightness might vary from star to star. And also, we want to make sure that every sample has the same scaling. So after we do this, we will have a clean curve which will look like this. Now, as you can see, we remove the variability. We remove the points which were beyond 3 sigma, which were beyond 3 standard deviation of the curve, like these points on the top. Now, it is important to note that we do not remove the points below the curve because they might be the dips caused by planets. And as you can see in this curve, we have small dips, and those are actually the dips which are shown here. If you zoom into that light curve or nice dips that is shown here, so we want to now look at those dips, and we want to have a system that can observe them and tell us if there's a planet present or not. And also we normalize the curve, as you can see. Now, one important thing to note here is that we don't only look at the dips. Because a dip can be caused by noise or something, right? So we also want to look at other factors like how periodic is the dip. Now, if something is periodic, we know that it is caused by no bad noise. And that is actually a big sign that if a dip is caused on a fixed amount of period, that there's something revolving around the star, and it is caused by in most cases some sort of planet. Now, before we can use this time series for the machine learning analysis, the first step would be to generate the generalized time series features from it. By generalized features, I mean features like mean of a time series, standard deviation of a time series, and so on and so forth. So for this, we don't use them, we don't calculate them one by one. We use this library called tsfresh, which will generate nearly 800 features for each time series you give. And you don't have to give a light curve. You can give any time series, any time series data you have. So this library is basically there to find out all these features for any time series. Now those features were then scaled and used to train a gradient boosted tree model. To give you an overall picture, the workflow. We started looking at a star, and we have a raw light curve like this. We then process the curve, and the clean curve look like this. It's a flat, very nice looking curve, but we still cannot use directly this curve. Then we extracted time series features from it, and that feature array is then scaled. And then finally, we use the scale feature array to train a classical machine learning model, and like something like gradient boosting trees, something using a tool called XGBoost will also work. Now let's see what kind of results we got here. So the first step was in the first step we used a simulated data set, and in our training set we used. Our training set had 6,000 samples. Out of those, 3,000 of those had planet signals in them, and our test set had 2,000 samples. Out of those, 1,000 of those cases were had planet signal in them, and our goal was to train a model which can find out those planet signals in the test set. So with this, we got our model predicted with an AUC of 0.92. Now, what this means is that 92% of the times the model ranked a planet signal higher than a false positive. We had a recall of 92 as well, and what that means is the model was able to identify 92% of all the planets present in the test set of 2,000 cases. Now, our model predicted with a precision of 94. That means that 94% of the predicted planets were actually planets, and that also means that 6% were not planets, and hence we say that there is 6% for false positive when the precision is 94. Now, if we talk about the precision recall trade-off, I would say that we want to optimize our model for a higher recall, because we don't really care about the precision. If we have, let's say, more false positive, that's okay. But we want to make sure that we do not miss any planets in the data. So if we have, let's say, even 20% false positive, that is okay with us. So in next step, we would optimize the model for a higher recall. So let's take a moment and talk about how do we find our planets now. So there's a method called box least squares, or BLS. BLS is the conventional way to find our planets. So what BLS does is we do the same step until this point, and after cleaning the curve, we try to fit a box function here, and based on how well the box function is being fit. As you can see here, this green line is the box function we are fitting. Based on how well the box is being fit, we will comment if there's a planet present or not. Now, I believe that this is not the best way to do this, and we should have a more smarter way. Instead of just fitting a box, we should have a smarter way to find out if there's a planet or not. And so I compared the results of BLS and the machine learning model on the same test set. And with this, I found out that BLS detected 84% of the planets in our test set, as opposed to 92% by the machine learning model we have trained. Now, this served as a proof of concept, as in we now know that machine learning is a way is also a decent way that we can solve such problems. And maybe it's a good idea to move away from fixed ways like this, where we have to figure a box function every single time. We should machine learning can be a smarter way to do the same thing. And maybe with this we will find out more planets that we could not find before using the BLS method we discussed. Now, the obvious next step here would be to apply the same on a real data set. And now in the current data set, this is in the current real data set, we had our data set was 15,000 cases, and out of those 3,600 were confirmed planets. And we want to make a model that finds out as many of those as possible. So now doing the same thing with those 15,000 samples as well. We extracted the time series features as using the TS Fresh. Doing the same workflow. And after doing this, before training the model, I actually trained a TSNE. And then I made this plot as you see on the right hand side. So now in this plot you can see that the green points are the points which has a planet signal in them, and the other points are points without a planet signal. And as you can see that most of the green points are clustered in one region of the space. So the way we should interpret this plot is so similar points will be clustered in one region of the space. So this is also a nice thing because by looking at this plot, we can tell most planets, most cases with a planet signal in them, are clustered in one region of the space. That means the feature generation part that we have done is not wrong. If the feature generation part was wrong, this would not be the case. Or let's say the features are not. If features do not provide enough information about the problem we are trying to solve, then the TSNE might not be able to see if they are similar or not. So in this case, this also is a validation step for the feature generation that we have done. And now we want to train a model which can do the same, and which can identify those planets, and which can basically tell us if the time series has a planet or not. Now, what kind of results we got? We got an AUC of 94.8. That means that this time, even actually, it's even higher AUC, and almost 95% of the times, model rank the planet signal higher than the false positive. We had again a slightly higher recall of 96. That means we identified almost all the planets cases present in them. We found out 96% of all the planets. This time the precision is lower, and this is because the model is already optimized for higher recall, as we want to find out as many planets as we can. Now we should also compare this with the state of the art. And back into 2018, the work done by Shalu was the best is the best known result on this problem. And comparing their results with us, we can see that the AUC they had is higher, the recall they have is slightly lower, and the precision they had is also higher than the precision we had. But we can also see that this is the model that they have used. We can also see that this is a pretty huge model, and it takes a lot more training time. And of course, if you need to hypertune the model, it will take even longer. It's also important to note that most of the work done after 2018 in this area is done based on this model you see on the right hand side. Basically, all the new works have some kind of use. Will use a model like this. And so everybody is following this state of the art results for that matter. Now, let me tell you the main idea behind this work. Now, we all know that the deep learning model can take raw data and then can automatically generate relevant features. For example, if you have a deep learning model like this, and if you give it let's say photo of a face, the convolutional layers here will automatically break down the photo into small features, and then the final part here, the fully connected layers here will then find out what features are actually crucial for the task or not. So the power in the deep learning model lies in this part where it, no matter what the data is, be it time series, be it image, it will break down the raw data into useful features. Now, if we can do this step on our own, and if we can generate features, generalized time series features, for example, then my idea was then we should be able to get similar results in a lot faster way, because then we don't have to train a heavy model. Which is why, instead of doing all this, my idea was to make sure that we have a way to make generalized features, and for that we use this library called tsfresh. And as we can see, the results we got are not so far off. They are kind of close. Now, let's take a moment and talk about how do we do planet detection currently in 2020. So we have a new satellite called TESS, and TESS was launched in 2018. And because it's a new satellite, we don't have many confirmed cases. So if we train when we train a model on this, we only had 16,000 curves and only had 500 confirmed cases in those curves, and that is like 3% of the 3% planets in the entire data set, and that is a class imbalance of 32 to 1. That means that for every planet present, there are 32 non-planets present in the data set. Now, this model you see on the right-hand side is a variation of AstroNet, and we will compare the results on this data with the time series analysis method that I just discussed in the last slides. Now, if we choose a standard threshold, as in of 0.5, as in if the prediction probability of the model is more than 50%, then we will call this case. We will call this case as a planet signal. If it's not, if it's below 0.5, then we will call this as a non-planet case. And if we take that standard threshold, we will have the following results. So as we can see, the model, the big model you see here, produced an AUC of 0.98, which is pretty high. A recall of 0.5, which I would say is very low, and because we are missing half the planets present in there, and a precision of 0.7. As opposed to this, our model produced an AUC of 0.8, a recall of 61, which is higher than the last case, and a precision of 83, which is also higher than the last case. But now we don't have to follow the default threshold of 0.5, and we can change the threshold for our case as well. As in, we can choose a threshold which has the best recall, and a best recall and a reasonable looking for precision as well, because we don't want super low precision, because then we will have most cases as the false positive cases. Now, looking at the case with the optimized threshold, now for the big model, we have chosen the threshold. The best threshold was 0.1, and we do not have the AUC for this. The recall was a lot higher, 0.89. On the other hand, the precision is super low. It's 0.44. That means that 56% of the cases found out by the model are not planet signals. That means we have a lot of cases that more than half of the cases will not be planets, which is not the best scenario for us. And on the other hand, for our model, the ideal threshold was 0.12, and we got an AUC of pretty much the same, 0.8, a recall of 0.82, which is nice, but still lower than the best recall here. On the other hand, the precision is also pretty good, of 0.81. So here we can see that the big model is not performing so well, and of course the big model took a lot more time for training and stuff. But in this method, we can see that that the smaller model where we make generalized features beforehand, and when we just train a simple XGBoost model, will work. Will actually produce a higher recall here, and actually a higher precision here. So, but we have seen that both the models, small or big, both the models are now performing significantly worse. And now why is that? Like, we are not getting proper performance of this level. And the prime reason, I believe, is the high class imbalance, which is 32:1. And I believe once the class imbalance is fixed, both the performance will have results of this range. Now, the other main point is that the new curves we have has lower amount of points in them, and which means that we have less information in the new curves we have, which also might be a reason why we have a lower performance with both the models, smaller or bigger. And as we have seen, the gradient boosting method works better in some cases than the heavier deep learning model. Now, going forward, if we try to look at the pros and the cons of the method that we have introduced here, we know that the machine learning model is much faster. Our model can be trained in 5 minutes and two CPU system, and normal PC these days have actually more computation power than that. So pretty much everybody can train it on their computer. You don't need a supercomputer or a special hardware like a GPU to do that. And it will save a lot of time. You can try and test new things and change something if you don't like, and so on. On the other hand, Astronet took 5 hours to train on a GPU. And if you need to hypertune the model, because there's a lot of hypertuning to be done, it will take a lot longer. On the other hand, we can use the exact same system, exact same code if we use it for tests, or if you use it for some other source. So if tomorrow we have a data source which has a different number of points in the series, in the time series, we can just use the same system, because in our system, what we make sure is that no matter what the time series is, TS-Fresh will always make the same amount of features, and based on those we can even use the same model that we have trained for other time series. However, this is not the case for the deep learning models, because for this data set, the model is smaller. Now, for the test data set, we had to actually change the structure of the model as well. So we cannot really reuse them in that sense. On the other hand, the cons are the following: that now we need an extra step. With the deep learning model, we can just provide the time series into it, and it can automatically generate features. For example, here we don't need to calculate that the TS-Fresh step, so we have to do an extra step. And the other part is the lower performance. So the state of the art is actually this big model that you see here. And if you have to use one model, and if you have enough time and enough computation power, the bigger model like this is the way to go, because those models are they can learn complex things that normal machine learning models might not be able to learn. So, but if you have the time and money, you should always go for a model like this. And it is a known thing that the classical machine learning models do not lead to the best results. Especially if you are trying to solve, let's say, speech recognition or something else, if the problems become complex, the classical machine learning might not be able to do it, unless you are able to generate somehow features which can convey all that information. But that can become really hard. So the final takeaway is that most people, when they start machine learning, they just take a big deep learning model, and they just start to tweak it and then change it. But then, first of all, it's really slow to do that. You have to change a lot of things, and that's not the best way to go about it. And we should still try a simpler model first. Especially the simpler machine learning models can also produce very good results, especially if the feature generation part is done right. And by that I mean most important information for the task should be conveyed in the features that we generate. It can be image data, it can be time series data, or any data. I think before starting with big heavy models, or like the best performing models, and try to tweak it, we should still try a simple machine learning model first. And once we have some insights into it, and because simple machine learning model will not take much time. You can train one model in 5 minutes or less. And once we have some insight into it, we can of course switch to a deep learning model, or if we have time and if we have the money, we can also switch to a bigger deep learning model. And second is that if we are trying to solve business problems or scientific problems like plant detection or fraud detection and so on, the machine learning is a decent way to go about it, because the other solution like BLS might not be the best way to go about it. And machine learning can actually give us, as you have seen in this case, more planets than BLS. Similarly, if you let's say tackle fraud detection or something similar, you will be instead of going by rules, going by basic rule-based system. A machine learning, even classical machine learning systems can produce smarter and faster solutions. So with that, I hope that you use this in your work as well, and I hope that this will help you to try and test things faster, and hope that this will accelerate some of the projects on your end as well. This is my main the main research that I have followed for this work. And if you have any questions, feel free to ask. You can always email me on the email given below. Thank you.
Hey guys. So the first question is, how is the data fed into the model? Is it 1D or 2D? So data is fed as 1D. It's a feature array of 800 time series features, as we discussed in the presentation. And the second question is, have you considered adding some residual connections? I've not considered that yet, but other people have tried LSTM blocks, and which is not exactly the same thing, but those didn't perform as well as the convolutional astronaut that you have seen in the presentation. So still after using the LSTM cells, the astronaut based model is the best way to go forward. But other people are trying those things, and the results are similar, but slightly lower than that, slightly lower than the convolutional based astronaut that we have. If you have any further questions, please post it below, or you can also reach me online on the email. I will be happy to answer any further questions or suggestions that you have on this work. Okay, I see there are no further questions. So feel free to reach out on my email, as you see on the last slide, and let me know if this works helps you in any way as well. Thank you very much. Oh, there's a third one. Excuse me. The last question is, where can I get the data set that you have used? So this data set is online. If you Google NASA archived test data, then you will be able to download all sorts of process data sets of tests as well. And one of those data sets is what I have used as well. And if you like, I can also send you a link of the exact data set that I have used if you want to try something. In that case, you have to send me an email, so reach out to me somehow. I will be happy to share that and work together on this. Thank you very much for listening.